Boa tarde a todos a mais seminário dos Colóquios de Coordenação de Astronomia e Astrofísica do Observatório Nacional. Estes são seminários, colóquios regulares que acontecem quase sempre todas as quintas-feiras, 3 horas da tarde. O próximo seminário, na nossa agenda de agosto, na próxima quinta-feira, 13 de agosto, 15 horas, com cosmologia numérica e observacional, usando a biblioteca Num Cosmo, do Dr. Sandro Vitenti, da Universidade Estadual de Londrina, daqui do Brasil. E nesta oportunidade, a gente vai apresentar a doutora Romina Petrucci com Transiting Exoplanets from the Search of Orbital Decay to the Discovery of Earth-like Worlds. Então, desta forma, a gente vai mudar agora o idioma para o inglês, já que ela é da Argentina, e deixem-me apresentar ela. Dr. Romina Petrucci is an assistant researcher in Argentina working at the Observatorio Astronómico de Córdoba. Her mainly interests are the detection and characterization of planets using the transit technique, and also the characterization of host CNSR planets through spectroscopic and photometric methods. Romina obtained her PhD in 2015 from the Universidad Nacional de Córdoba in Argentina, followed by 2 postdoctoral fellowships, one at the Observatorio Astronómico de Córdoba in Argentina and at the Instituto de Astronomía of the Universidad Nacional Autónoma de México. In 2016, she won a fellowship from the Carnegie Institution for Science and Richard Lounsbury Foundation to work at the Las Campanas Observatory in Chile. So this way, we welcome Romina to begin with her talk today. Thank you, Romina, for being with us.
Thanks, Jimena. Okay, I'm gonna share my screen now.
Yeah, thank you.
Okay. Okay, perfect. Can you see the screen?
Yeah.
Yes. Okay, perfect.
Thank you.
Let's start. Okay. So, well, hello everyone. Thanks for inviting me to give this talk. Unfortunately, I don't speak Portuguese, so this talk is going to be in English. So as Jimena mentioned, I am a researcher at the Observatorio Astronómico in Córdoba, Argentina, and also a member of the Consejo Nacional de Investigaciones Científicas y Técnicas in Argentina. So this talk will be split in 2 different parts. In the first part, I'm going to talk about a project I started 4 years ago to search for orbital decay. And in the second part of this talk, I will introduce the Syntex project in which I have been involved for the last 2 years. Okay. So here I show you a plot of orbital period versus planetary mass for the more than 4,000 exoplanets confirmed so far. So different colors here indicate different detection methods. Among them, we have transit, radial velocity, microlensings. And given that the results I'm going to show you later are related to transiting exoplanets, I'm going to focus specifically in this technique and how it works and on the information we can get from it. So I show you here a plot of the cumulative number of planet detections as a function of the discovery year. Here again, you can see in different colors the different detection techniques. And I want you to put more attention on those detections corresponding to the transit and radial velocities. Here, transits are marked in green color and radial velocities in red. So as you can see, around 2009, we have like a breakpoint. After 2009, the number of detections with radial velocities and transits were more or less the same. But after 2009, we have like an explosion of transiting exoplanet discoveries. And this was thanks to the first results provided by the space mission Kepler that was launched in 2009. So in this table, I list the most important detection methods, and you can see percentages. And well, as you can see, around 76% of the planets we know so far were detected by the transit technique. So we can see that this technique has been the most successful exoplanet detection method by far. So, okay, let's address now the question, how does the transit method work? So to answer that, we first have to understand what the planetary transit is. So suppose that we have a system formed by a star and a planet, and the planet is orbiting around the host star. Suppose that the star in this case is this yellow-orange circle, and the planet is the blue, small circle. So suppose that the orbit orientation is such as that the planet passes in between the star and the observer once every orbit. So in this case, when the planet passes in between the star and the observer, it's going to block part of the stellar light, producing this dip that we can see here in the light curve. So one of the things that make this technique beautiful is that from the shape of this dip or the transit, we can estimate the inclination of the system and also the size of the planet relative to the size of the star. And we can obtain another important quantity that is the mid-transit time. This is the time at which the transit occurs. So, and it is important because if we take measurements of the mid-transit times at different epochs, we might be able to answer to point out two different important points. One, if that we can infer the presence of extra planetary mass bodies in the system that can be gravitationally bound. And we can also know whether or not the planet is going to be engulfed by its host stars, for example, by analyzing orbital decay. So, and we can assess these 2 points by using the technique named as transit timing variations. So let's talk a little bit about these 2 points. Let's talk about the additional planets. So suppose that we have a system formed by a star and a planet. So in that case, the planet will describe a purely Keplerian orbit. This means that each transit of the planet is going to happen at the exactly same period, not earlier, not later. So if you see here, for example, on the right side, we have this cartoon. These are the transits of a particular planet, for example, and the blue mark correspond to the observed mid-transit time. So what we'll see is that the observed mid-transit times will be all coincident with the expected mid-transit times indicated here with this red line. So, but what happens if in the system we have the star, we have the planet, but we also have a perturber, for example, planetary mass companion. So in this case, the gravitational interaction between the two bodies are going to produce an acceleration of the movement of the planet in one orbit and a deceleration of the same planet in another, for example, orbit. So what we'll see, again, let's see the cartoon on the right side, we see that sometimes the transits will happen earlier than expected, and sometimes the transit will happen later than expected. So if we connect all these mid-transit times, we can see, as I indicate here with the solid black line, like a sinusoidal modulation. And this is very interesting because in most of the systems in which we know that we have transit timing variations, we see this kind of effects. So let's see some examples here. Well, in this case, I show you what we call O-C diagrams. This kind of diagrams has in the x-axis a measurement of the time, for example, the phase or bisected Julian dates. And in the y-axis, what we have is the difference between the observed mid-transit time and the calculated mid-transit time. And when I say calculated mid-transit time, I mean the transit time computed by the ephemeris. So you can see here that most of the variations looks like sinusoidal, but we have also some irregular variations. And so far we have a few dozen of planets detected and characterized by this transitive mean variation. Here on the left, I show you the case of the system Kepler-9. This is very interesting because this was the first planetary system found by the transit timing variation techniques. So the system is formed by the star and two giant planets that place almost in the 2.1 mean motion resonances. So, well, another important phenomenon that we can assess with the measurement of the mid-transit times is orbital decay. So suppose we have, again, we have the star and we have a short period planet around it. So in this case, given that the planet is so close to the host star, it's going to be subject to strong tidal interactions that are going to entirely dominate the tidal evolution of this planet. So in the case we have that the rotational period of the host star is larger than the orbital period, is going to be a transfer of angular momentum from the orbit to the stellar spin, provoking a reduction of the semi-major axis over time. This is what we call orbital decay. So let's see now again in this cartoon on the right, how interpret this in terms of the mid-transit time. So given that the orbit shrinks, so the period decreases and the transit will happen earlier and earlier and earlier than the expected time. So what we see is a kind of quadratic or parabolic behavior of these times. So, so far we only know two giant short period planets candidates to present orbital decay. I'm going to talk a little bit about each of these planets. On one hand, we have WASP-12b. This is a planet with masses of 1.4 Jupiter masses and an orbital period of around 1.1 days. So on the right side, you can see the O-C diagram from a work of Maciejewski et al. So these authors propose three different mechanisms to explain these observations. So the first mechanism is orbital decay, here indicated with the solid red line. They also propose apsidal precession, pointed out here with the blue line. And they also propose the presence of a companion to explain this plot. Well, on the other hand, we have the case of WASP-4b. This is also a giant planet with a mass of 1.2 Jupiter masses and an orbital period of 1.34 days. On the left, we can see again the O-C diagrams for the primary transits and in the top panel, and for the occultations in the bottom panel. You can see again this like quadratic, this parabolic behavior, and the same mechanisms proposed for WASP-12 were proposed for WASP-4 to explain these observations. So now that we have a more general picture of how orbital decay works, let's go back to the plot of period versus planetary mass. So here, this rectangle highlight, so one of the well-differentiated exoplanet populations, the populations of hot Jupiter-like planets. This is composed by planets with masses larger than 0.1 Jupiter masses and orbital period smaller than 10 days. And these planets are very, very interesting because they represent a challenge for the theories of formation and evolution of planetary systems. So in fact, there are several works that have demonstrated that many of these close-in planets will spiral in toward their host stars and will be destroyed. So, okay, with this idea in mind that there are plenty of short period planets that might be suffering some shortening on its orbital period, in the year 2016, we started a project whose main goal is to search for evidence of orbital decays in short period planets orbiting around stars from the south hemisphere. So the methodology we use is to perform systematic and continuous observation of the primary transit of these short period planets and to measure precisely the mid-transit times. So currently our sample is formed about 10 targets with orbital periods smaller than 2 days and planetary masses larger than 1 Jupiter mass. And the observations are mainly performed by 2 Argentinian telescopes. One is the 2.15 meter telescope at the Complejo Astronómico El Leoncito in San Juan. And the other one is the 1.54 meter telescope at the Estación Astrofísica de Bosque Alegre in Córdoba. So, okay, so far we have obtained results for 2 of the targets of the planets in our sample, but today I'm going to talk about the results we obtained for WASP-19b. So, first of all, we can say that WASP-19b is a hot Jupiter-like planet, which is orbiting around a main sequence G8 star. It's a giant planet, so its mass is 1.1 Jupiter masses. The radius is around 1.3 Jupiter masses. And the most important characteristic is that its orbit around its host star each 19 hours. So on the left here, I show you the transit-like curve folded with this 0.78 days period obtained from the Super WASP survey data. And on the left, you can see also the light curve, but in this case, folded with the rotational period of the star WASP-19, which is around 10.5 days. So we can see that WASP-19 is in fact an active star. So, okay, what we knew about the orbital decay of this exoplanet. So according to the computations performed by Matsumura et al. In 2010, the total angular momentum of the system is smaller than a certain critical value that depends on the masses of the star and the planet, and also on the momentum of inertia. And they say that the orbit of WASP-19b is in fact unstable, and we should expect that the planet might be suffering orbital decay. So when the planet reaches a certain limit, this will be tidally disrupted. So, and here I am going to talk about the previous result, observational and theoretical. So regarding the previous observational results, in a work of 2013 of Mancini et al., they analyzed 54 transits. They found that the alinear ephemeris is not a well fit to the mid-transit times. So in fact, they find a reduced chi-square of around 2. But they say that this huge value for the reduced chi-square is because an underestimation of the mid-transit times, the errors in the mid-transit times. So later, Espinosa et al. In 2016 analyzed 60 transits, the 54 transits of Mancini and other 6 transits, and they found that there is a systematic difference of around 40 seconds between the data of 2014, 2015, and the data of 2017. And they say that given that their mid-transit time errors are at most 10 seconds, the difference of 40 seconds is in fact significant. So regarding the theoretical predictions, there is a work of Balsecchi and Ratio of 2014. And they say that as a result of the orbital decay, after 10 years of observations, we will be able to detect a shift in the mid-transit times of 34 seconds for WASP-19b. And later, Asik and Wimberg estimate that after 1 decade of observations, the shift in the transit arrival time should be of around 200 seconds. So in order to elucidate if WASP-19b has a measurable orbital decay, in 2016, we started the observations of the primary transits of this system. So here I show you, well, the 12 transit-like curves that we obtained from 2016 to 2019. And well, here in red and orange colors, I show you the transit that we observe with the facilities I already mentioned, at the Casleo and EAVA observatories. Here in blue, you can see the only one transit that obtained one of our collaborators in Australia with a telescope of 30 centimeters. And in green, you can see here 2 of the transits we observed with another telescope of 30 centimeters, the Fram telescope in the Pierre Observatory, also in Argentina. Okay, so besides our 12 transit-like curves, we gather from the literature other 62 transit-like curves acquired between 2008 and 2019. So in total, we had a full sample of 74 transits covering a time range of 10 years. So if you remember this number, exactly 10 years of time coverage is the amount of time that we need to compare the observations with the predictions. So what we did was to use the usual methodology. So we took the mid-transit times as a function of time, and we fit 2 different models, a linear model and a quadratic model representing linear and quadratic ephemeris. So in the case of the linear ephemeris, we suppose that the orbital period is constant. Here E represents epoch, T-ref the minimum reference time. And in the case of the quadratic ephemeris, we suppose that the period changes in a steady rate. So in the table, you can see the results of our fits. So I want you pay attention here to the variation of the period with the epoch. You can see that the value that we found is really a small quantity. So in fact, if we translate this parameter into a more intuitive form, let's say the variation of the period with the time, we can see that this value is consistent with 0. So, okay, here I show you our O minus C diagram. In the x-axis, we have the epoch, and in the y-axis, we have the difference between the observed mid-transit times and the calculated mid-transit times through a linear ephemeris. So again, the colors here represent our observations, the observations taken by our group, and the gray colors represent the data taken from the literature. So after a careful inspection of this figure, you can realize that there is no quadratic pattern that might indicate the presence of evidence of orbital decay in the system. However, we need the statistic to confirm this result. So here I show you 4 of the most useful and widely used metrics in this table. So we have, in this case, starting from the left, the model. Then we have the reduced chi-square, the residual root mean square, the Bayesian information criterion, or BIC, and the Aikake information criterion, or AIC. So as you can see, the reduced chi-square and the big values favor the constant period model over the changing orbital period scenario. However, if we see the IC value, we will realize that it gives support to the quadratic model over the linear one. So here it's important to notice that the evidence in favor of one or another model is not strong, because the difference between these values are really small. So the discrepancy mainly arises because, if you remember, the value that we found for the quadratic coefficient is really small. So we could say that both models, the linear and the quadratic one, are representative of a linear ephemeris. So as a first conclusion of this work, we can say that the evolution of the mid-transit times over 1 decade is best explained by a constant orbital period. This means that we didn't find evidence of orbital decay. This contradicts the predictions. Okay, so finally, besides the null detection of orbital decay, this kind of analyses are important, are useful, because they allow us to understand what happened with the evolution of these short period planets. And we can do this through the measurement of this quantity called modified tidal quality factor that is defined in this way through this equation. And it is defined in terms of the maximum tidal energy stored relative to the tidal energy dissipated. So if we have small values of Q, we can say that we have an efficient tidal energy dissipation and hence a fast orbital evolution. And if we have large values of Q, the tidal energy dissipation is inefficient and the orbital evolution will be slow. So for WASP-19b, we computed this value and we obtained a lower limit of Q of 1.2 millions. On the right side, I show you a plot of the effective temperature versus the logarithm of Q. You can see here the blue point indicate the result of this work. And in red, we can see the values estimated in some previous works for WASP-19. And also in gray, in open symbols, we have the Q values computed by Penev et al. In a theoretical work for 75 hot Jupiters. Here, the arrows represent lower limits of Q. So in general, the values of Q span in a really wide range from 10 to 5 to 10 to 12. So we can see that our result is in agreement with previous studies. So as a conclusion of this first part, we can say that we found no evidence of orbital decay in WASP-19b. So the evolution of the mid-transit times over 10 years is better explained by a linear ephemeris. And on the other hand, given that there is this wide range in the values of the modified tidal quality factor, it is really important. We need empirical model independent estimations of these Q values derived directly from the observational data to really constrain this quantity. So, okay, so in the last 15 minutes of my talk, I'm going to introduce the SciTeX project. So in this case, SciTeX is an acronym for that stands for Search and Characterization of Transiting Exoplanets. So Scientex is run by the Scientex Consortium and the Universidad Nacional Autónoma de México. The Scientex Consortium is formed by the Center for Space and Habitability at the University of Bern, the Planet S Group, the University of Cambridge, and the University of Geneva, and it also receives the support of the Antoine de Saint-Exupéry Youth Foundation. So, well, what are the scientific goals of Scientex? Well, it has two main science goals. The first one is the search for terrestrial planets orbiting around ultra-cool dwarfs through the acquisition of a very precise time series photometry. And the second scientific goal is to provide ground-based support for the ESA CHEOPS space mission. So here I present the names of the people that are part of the Scientex scientific team. The principal investigator is Dr. Brice Olivier de Maury at the University of Geneva. And also we have the co-PI and coordinator in Mexico, Dr. Gilén Gómez Maqueochu. And also we have associate researchers, postdoc, and student as a part of this collaboration. In fact, well, I evolved in Scientex during my postdoc in Mexico. And as a part of my task, I participate in the commissioning, in the preparation of the observations and in the observations themselves. So, okay, let's take a look at the instrumentation of Scientex. So this is a 1 meter Ricci-Chrétien telescope. It has been installed at the Observatorio Astronómico Nacional in San Pedro Mártir in Baja California, Mexico. So it's equipped with an Andor Icon camera, and this is very important because this camera is really sensitive to the radiation coming from red wavelengths. So it also has filters, a wheel of filters with broadband filters, blue blocking filters, near infrared filters. So the field of view is quite small, and we ended the commissioning in the last year during March. So here I show you some of the pictures we took for Scientex. Here we can see the interior of Scientex, and here the surroundings with the sunset in the back. Okay, so I'm going to focus in the first of the scientific goals. So the question is, why do we study ultra-cool dwarfs? So first of all, it's important to say what an ultra-cool dwarf is. So the main characteristics are these. So these are late type M stars and also brown dwarfs, substellar objects. Their spectral types are later than M7. Their effective temperatures are lower or around 3000 degrees Kelvin. The radius are in between 0.1 and 0.35 solar radius, and their masses between 0.01 and 0.08 solar masses. These stars or these objects have fully convective interiors, and given that their effective temperatures are so small, they mainly emit in the near infrared. Well, also in a work of Cantrell et al. In 2013, they found that around 50% of the astronomical objects near the sun are ultra-cool dwarfs. So, okay, so the last few years had been recognized that the formation of planets around these environments is very important for several reasons of advantages. The first reason is that it's easier to find small planets around ultra-cool dwarfs than around, for example, G dwarfs. This is because the transits of small planets around ultra-cool dwarfs are deeper, and even the amplitude of the radial velocities are larger. So on the other hand, something important is that given that the equilibrium temperature scale with the luminosity, the habitable zone is closer to the star. So this is important for atmospheric characterization. For example, if we have a terrestrial planet. Also, the number of super Earth-sized planets increases with the decrease in effective temperature, specifically for those with orbital periods smaller than 50 days. And finally, according to the core accretion theory, so this formation of planetary, this formation of model formation of planets, we have that the protoplanetary disk around ultra-cool dwarf have not only a low mass, but also have a small sizes. So this means that these objects will be ideal candidates for hosting terrestrial planets. And here I show you an illustration of the first planetary system discovered around an ultra-cool dwarf, TRAPPIST-1. This is an M8 star, and we have 7 terrestrial planets. So this discovery was like a validation of this core accretion theory in the sense of in the context of the ultra-cool dwarf. So, well, let's talk now about the first science discovery. So, a multi-planet system around a late type star. So, the first contact we have with this object was through when we realized that the Test Science Office issued 2 alerts indicating 2 planetary candidates around the star TOI 1266. This is an M3 star, and this planet with orbital periods of 11 and 12 days. So they were observed with the mission test in sectors 14, 15, 21, and 22, as I show you here. You can see in black, this is the test light curve without removing the systematics. The orange line here is the trended model, and the green light curve here shows the test light curve after removing the trending model. So if you can see here, the red triangles indicate the position of the transit of the planet B, and the blue triangles indicate the position of the transits of planet C. So, okay, what we did was to observe this star with Syntex, and well, these are the first transit we obtained for both planets. So this allows us to confirm that the transits are effectively produced around the late type star that was first pointed out by the test office. So as you can see here, these are shallow transits. So the planets are small planets. In the case of the planet B, the radius is around 2.4 radius. So this is a sub-Neptune. And in the case of TOI 1266c, the planetary radius is around 1.6 radius. So this is a super Earth. Here I put some information about the orbital period, but also the masses, but I'm not going to talk about the masses or the estimation of the masses of this planet in this opportunity. So we also include additional data from photometry, from high resolution spectroscopy and high angular imaging. So regarding the ground-based follow-up photometry, we acquired 6 new transits of planet B. You can see here the transits acquired at different facilities. You can see the name of the facility and the filter in which they were observed. And also we collect data of high resolution spectroscopy, so to discard false positives and also to perform a characterization of the stellar host. We use the TRES spectrograph and the higher spectrograph. And Also, we use high angular imaging to discard false positive signals due to, for example, unresolved binaries, blended stars, because, well, the size of the pixel in text is really big, it's 21 arcseconds. So in this case, we use the Astralux and Sharks instruments. So, and finally here, I want to show you the main results of this work. And you can see here the plane of orbital distance versus the planetary radius. The black squares represent the planets B and C. And also you can see here crosses of different colors. So this corresponds to the position of the planets, of simulated planets after 10 gigayears, after running the Bern evolution model. In this case, what we suppose is that this is the result of the long-term thermodynamical evolution of these planets under the effect of the extreme ultraviolet flux of its host stars that produce an atmospheric photoevaporation. So in this model, we suppose that the planets are formed or consist of a solid core plus an envelope of helium and hydrogen. So you can see here that both planets are placed on both sides of the radius valley. The radius valley is this dirt that is clearly shown here of planets with radius of around 2 Earth radius. So you can see that planets above the radius valley retain some of the helium hydrogen atmosphere, and that those planets located above the radius valley can be considered as bare rocky cores. So in this sense, TOI 1266 is very interesting because in this case, the inner planet is larger than the outer one. And in the context of the photoevaporation, this can be perfectly explained because the inner planet is more massive, so it's able to keep some of the atmosphere, even if it is closer to the host star. So as a quick conclusion, we can say that planets in multiple systems with this similar radius as we have in this situation are key to understand the origin of the radius valley. I only talk about photoevaporation, but there are other mechanisms proposed to explain this radius valley. And here are the general conclusions. So when I put the conclusions about orbital decay, but about SINTEX, what we can say is that the instrument is capable of provide very precise photometric observations to detect Earth-like planets around ultra-cool dwarf. Also, I didn't talk much about it, but we need high precision photometry and radial velocities to measure precise planetary masses. And finally, systems with different radii planets well, are ideal to understand not only the differential evolutionary stories of the planets in the system, but also to understand which mechanisms could explain the radius valley. For example, in the case of photoevaporation, the question is if this mechanism can explain the existence of these two planets in the same system. So, thank you very much. And finally, I want to show you, before the questions, I want to show you a video, a time lapse of SINTEX. Here, it's like a SINTEX in action. You can see it's a video recorded by Paco Guillen. And well, you can see all the sky moving for, well, around, I think, 6 hours. There are a couple of satellites. And well, that's it.
Okay, thank you very much, Romina, for this wonderful talk. I don't know if it was my computer, but I didn't see any video.
Oh,
I don't know
okay.
if it was my
Me
problem.
Okay.
Okay.
I can show you
So
the video again.
nobody saw.
Oh,
So
sorry.
please show us again.
Okay. Let me share the screen again.
Okay.
Okay.
Now I think that we are going to see something. Yeah.
Do you see the syntax
Yeah,
now?
we are seeing now. Yeah.
Okay, perfect. Okay. So I think this is a video of around 6 hours.
Okay.
Well, I think it's really beautiful. So that's it.
Yeah, thank you.
A short
Thank you
video.
very much.
Thank you.
It's-
Thank you.
Thank you for your talk. Was wonderful. So
Thanks.
now I think we are open to questions.
Mhm.
I don't know, Armando, if you have some. Por favor, pessoas, lembrem que podem fazer as perguntas em português. A gente traduz para ela. Se alguém souber falar espanhol, a gente também faz as perguntas para ela. Armando, você tem alguma pergunta?
Sim. Jimena, dos comentários no YouTube, teve uma pergunta do Andrés, mas curiosamente foi respondida quase imediatamente depois que foi formulada. Então, por enquanto, não estou vendo, não.
Não tem perguntas?
Não.
Você se incomoda, Romina, se a gente continua devagar, mas falando em português, para as pessoas talvez ficarem mais à vontade para falar?
Isso.
It's okay. You can continue speaking Portuguese.
Okay.
I understand.
Ok. Então, eu tenho umas perguntinhas para te fazer.
Okay.
Você mostrou sinais de OMC, de Orbital Decay, e a amplitude desses sinais eram de aproximadamente 1 minuto, se eu não vi errado, 2 minutos. Então, a minha pergunta é, a gente consegue fazer esse tipo de medições?
Okay. Yes. Oh, so okay. So the question is if we are able to obtain the precision of this measurement. So in this case, yes, because the O minus C diagrams that I show you correspond to works with observations that come from ground-based instruments. So in this case, yes, we are able to obtain that precision. In the case, for example, in our O minus C diagram for WASP 19b, the errors in the mirror transit times are a little bit larger than usually because we use like a conservative approximation. In this case, we estimate the errors with different methods, with Monte Carlo and residual permutation to fit when we fit the transit. So in that way, we choose the larger error between the results of these two methods. So that's why, for example, in our case, the errors in the mid-transit time are a little bit larger. But for example, in the case of the work of Masirjejski or Bouma for WASP-4 and WASP-12, they use like another methodology. They perform a global analysis. So I think that's why the errors that they obtain are smaller. So there is an important difference there, but you need, of course, a bunch of observations to say, okay, there is a parabolic behavior or a quadratic behavior. So, well, that's...
Okay, so that works. They have observations from ground base also? Or
yes,
that observations are from Kepler or?
No, for example, in the case of WASP-12, all the observations are ground-based observations.
Okay.
And in the case of WASP-4, they have only one point that corresponds to the observation, to the transits observed with TESS. And in fact, they realized with the observation of TESS, they realized that there was a variation in the mid-transit time. And they continue observing the target, and they found that there is a systematic change in the mid-transit time that could be explained by orbital decay. But there are also some other mechanisms, as I say. So it's just like candidates to present orbital decay. It's not for sure the same.
But so sorry, because I confuse all the languages. But so with orbital decay, we are expecting signals of about a couple of minutes, or we can expect signals higher in amplitude.
So we will expect signals of in fact, it depends. So it depends of the system. So because to detect orbital decay, so you fit this quadratic model, right? So the quadratic coefficient in this case is what we provide information about the system, because enclosed in the quadratic coefficient, you have information about the mass, about the mass of the planet, the mass of the star, and it depends on many factors. I mean, it depends on the system, how much is going to vary the mid-transit times due to orbital decay. That's
okay. Okay. And another question relative to this, you said that the Q factor values are about 10 to 5 to 10 to 12.
Yes.
But where they are obtained from? We obtain that value from models applied to the solar system?
No,
or from where?
Well, all these values came from theoretical works. That is very important. So in different works, they do different assumptions. For example, some of these works use the prescriptions of Sun well, in this case, the work of Sun describe or explore the contribution in the evolution of, for example, closed binary of the tidal forces. So they base all the work on the prescription of Sun, and they obtain these values of Q. They are all theoretical. That's why in the last conclusion, I say that we need to obtain empirical values of Q. And this is very important, because with this wide range of values of Q, we don't know if what we obtain, it's okay, or we need to constrain these values. And well, there are some other works that they analyze what happened with the evolution of the planet if they suppose variations in the G modes of the stars, excited, for example, by the bulge in the planet, and well, so things like that. But this is what we have so far. It's not really understood, and that's why I put emphasis in the observations of this value of Q through measurements of mid-transit times, in fact.
Okay, thank you. I don't know if we have another question from the people from here, Zoom. Nobody?
Yes. There arrived a question from YouTube. Andres Galas asked, Romina, have you ever faced problems in observations due to Starlink?
No, not yet. And I hope we don't have any problem related to Starlink. No, not so far.
Okay. Thank you very much.
Thank you.
So, and if nobody's going to ask anything, I have one more question, and it's relative to the masses of the planetary system that you find with TESS and with the Project and X. You didn't talk about that?
No.
So I will ask you about that.
Okay, okay. So I don't know if you remember the masses of, I can share my screen again.
Okay.
Okay, let me just, can you see the presentation? Yeah, okay.
Yes.
So in this case, so the masses that we measure, you see here for the sub-Neptune planet, the planet B, is around 13 Earth masses, but if you can see that the errors here are really, really big, for example, and also here for the super Earth. So what we did to estimate the masses of both planets in the system, we use transit dimming variations. In fact, I have a slide for this. Okay, this. So here I show you the O-C diagrams of planet B in the top panel and from planet C in the bottom panel. So what we did is to run an N-body integrator, the KENGA, and plus a differential evolution Markov chain Monte Carlo. And in this way, we be able to estimate the masses of the planets in the system and also the eccentricities. And we perform an analysis of the stability of the system. And in that way, we were able to constrain the eccentricities. So both planets have very low eccentricities, but we were not able to constrain better the mass in this case. And that's why one of the conclusions was, okay, we need to estimate more precise masses with radial velocities or even with TTVs.
Okay, so that black points are the observed,
yes.
observed minus calculated TTVs that you take. 5
yes.
for the C planet and I don't know, 12 for the B planet. I don't know if I am seeing. So you didn't obtain transits between 15 and 150 in the time axis. Okay.
Yes.
Okay.
Yes.
But you didn't observe with a spectroscopical. You didn't make a spectroscopical observation. You didn't have radial velocities to constrain better this.
No. So we had. So we have a spectroscopic observations, but if I don't know if you remember one of the slides, the resolution of the spectrograph we use are, we will say 50 or 44,000. So this is not enough to perform an estimation of the masses of the planet. This is only useful to discard, for example, low mass binary companions or some other stars, but not for planets as small as these planets. So in this case, what we did was a statistic validation to confirm the planetary nature, the nature of the planet, but we didn't have the time to obtain the spectroscopic high resolution spectroscopic observations to constrain the masses. Simultaneously, so this paper was already accepted, but simultaneously another work was published with the same system, indicating that they obtained radial velocities for these two planets. And in fact, the curious thing here is that they were not be able to better constrain the masses than we did. So that was crazy. And well, that's what I can say about it. So I think maybe with this new spectrograph like Espresso, for example, we'll be able to obtain some, I don't know, decent radial velocities, decent radial velocity curve, for example, in this case.
So you plan follow up this system in order to make radial velocities observations?
So we haven't discussed yet that.
Okay.
Maybe yes. Well,
Okay.
maybe yes. For sure, we are going to continue observing the target with photometry, but I'm not sure about radial velocity.
Okay. Okay. Thank you, Romina. I don't know if we have any more questions.
I have a curiosity, Romina. Sorry,
Yes.
you have to.
No, it's okay.
Show a slide with the contribution from different telescopes. You show one, a small one from Australia that contributed just with one light curve. My curiosity to know why Australia is a problem of the telescope is so small, or was a collaboration, was a partial collaboration? Why just saw one light curve, one observational data?
Yes, no, in fact, we observe. So in this work, we usually use full transit light curves. We don't use partial transit light curves because there are many works that indicate that the mid-transit times are not well measured if the light curve is partial. So in this case, we had many other observations with this Australian telescope, but they were not full transits. So the problem is we have a difference in time. So because the observations are performed in Argentina and in Australia. So sometimes the ingress starts, for example, before the sunset, or sometimes we had the egress after the sunrise, or things like that. And that's why we couldn't have many transits with this telescope. But weather conditions are usually good. Well, at least in the place where the collaborator has the telescope.
I see. Oh, thank you very much.
Okay, Romina, so we appreciate very much this talk. Thank you for being with us today. Thank you for the time. Mas agora deixem só lembrar para vocês da próximo seminário, próxima quinta-feira, 3 da tarde, Cosmologia Numérica e Observacional, usando a biblioteca Num Cosmo, do Dr. Sandro Vitenti, da Universidade Estadual de Londrina. Então, dessa forma, a gente agradece. Thank you very much, Romina, for this talk.
Thank you.
And see you.
Thank you to all of you, and well, stay safe. So we see you.
Okay.
Bye.
Okay.
Obrigada a todos,
Thank you very
então.
much.
Até a próxima quinta.
Tchau.